Jill, can you hear me?
Yes, I can, Carrie.
Great, thank you. Well, good afternoon, everyone, and thank you for joining us for our first ever Michelin Scotland Innovation Park webinar in our Meet Our Tenants series. We're delighted to be presenting LERG to you today. I'm Carrie Cusick and I'm one of the project team for Michelin Scotland Innovation Park, or MSIP, which, if you didn't already know, is a massively exciting project to transform what was the Michelin tyre manufacturing plant in Dundee to an innovation campus for companies in academia operating in sustainable mobility and low carbon technologies. And if you want to find out more about MSIP, then of course you can check out our website or follow us at all the regular social media channels at MSIP Dundee. Before I introduce LERG, just a few housekeeping notes. Everyone will be muted as a default. If you do have any questions or comments, there are two options. You can either type your question in the question box, or alternatively, wait until the presentations are finished and use the raise your hand icon and you will be unmuted. And please be aware that once you've been unmuted, it seems to take a few seconds for the system to recognise that you are unmuted. So please just pause before starting your question so we don't miss the start of it. Today's webinar will involve a video and then we'll start the Q&A and the discussion. You should have received some documents via email yesterday explaining various TRL levels and other information. And so you should have had that. If you've not, let us know and we can arrange to get that to you. Today's session is being recorded and we'll share it on our social media platforms later today or tomorrow, and are also happy for you to share it with any interested parties. And as I mentioned just a moment ago, this is the first time we've done one of these webinars. And of course, we're hoping it will all run smoothly. But if there are any glitches, then please forgive us, and just thanks in advance for your patience. Now, moving on. LERG is a New York headquartered specialist chemical engineering business with a research facility in Dundee, Scotland. Today's session will feature LERG's roadmap for a proton-conducting ceramic hydrogen electrolyzer. On the call today, LERG's management team is represented by Rich Martin, CEO of Corporate, John Hughes, VP of Engineering and Business Development, Joshua Perkey, CEO of LERG UK, and Jeff O'Lear, Chairman of LERG UK. LERG's PCOEC electrolyzer plans to be the first of this technology on the market. And some of the key advantages to this technology that we'll learn about today are: when using renewable energy, it is a totally green process. PCC electrolyzers produce H2, therefore no additional energy is required to purify the H2 downstream. No expensive precious metal catalysts are required for PCC, so they are relatively inexpensive to make. And waste heat from other industrial processes can be used to heat the steam and the reactor to minimise costs. So without further ado, I'll hand over to my colleague Jill to run the video, and we can learn more of these exciting developments at LERG firsthand. Thanks, Jill.
Hello, my name is Rich Marin, and I'm the CEO of Low Emissions Resources Corporation. You should all have received our teaser titled Introduction to a New Green Hydrogen Technology. It looks like this. That teaser explains why hydrogen technology is becoming such an important market for the world's future. It explains the problems with current hydrogen technologies, producing cost-effective hydrogen at scale and on a distributed basis without the carbon pollution that exists today. It then explains why green, sustainable, and cost-effective hydrogen production is critical to the world. This goes on to lay out the importance of hydrogen synthesis through green electrolysis and the place that we at LERC believe the latest proton-conducting ceramics, called PCC, play in the drive for technological efficiency and commercial scalability in this important arena, and why this PCC technology improves on the foundation the existing hydrogen electrolysis technologies offer, as shown in this chart. This video is narrated by our technology leadership team, a team that's been working together since LERC's inception in 2014. While 2014 is when LERC began working on ammonia synthesis using PCC, LERC shifted to hydrogen as a critical first stage of ammonia synthesis in 2019, as shown in this diagram. This video will explain the extensive scientific knowledge base that LERC has accumulated in the past 6 years of ammonia and hydrogen research. This is embodied in our world-class and unique team of scientists working at our state-of-the-art research and testing facility, strategically located in Dundee, Scotland, near our academic partner and a leading electrolysis research center, the University of St. Andrews. It is at this Dundee facility that our scientists have reached what they believe is a technical readiness level of TRL 7 in the composition and fabrication of high-tech proton-conducting ceramic cells. The story of material science and ceramic fabrication leadership continues from Dundee to our installation in Southborough, Massachusetts, where, in partnership with Upstart Power, an SOFC company, we have built our electrolysis reactor stacks that have advanced the product development through the technical readiness level 5 demonstration, which we will show you today on this video. We are moving steadily and convincingly towards a TRL 6 milestone later this year, and that will be the seminal evidence of the commercial scalability of this important technology. Please enjoy our video presentation.
Hello, my name is Jeff O'Lear, and I am the Executive Chairman of our UK subsidiary, LERG. We are a research and development company with a world-class team of scientists and a state-of-the-art facility creating electrolyzer reactor technology that will produce green hydrogen through the use of SOEC proton-conducting ceramics. We expanded our research space from our initial collaborative lab with Professor Irvine at the University of St. Andrews in January of 2019. Our new Dundee, Scotland facility is a fully equipped state-of-the-art lab, allowing our team to rapidly iterate the R&D process required to solve the demanding problems on the road to commercialization. Our team is focused on the performance of our PSOEC cell by selecting the proper ceramic cathode and coating materials and optimizing the environment in which they operate. The facility allows us to develop a repeatable fabrication process that has been captured by our Quality by Design program. Developing scalable, repeatable processes on an efficient, durable cell that can be transferred to partners like Kyocera, Upstart, and VHE is critical for our success. Our downstream partners have the experience to help us further refine our technology. This collaborative approach will lead to a cost-effective, reliable stack technology, giving our PSOEC hydrogen electrolyzer an important position in the growing hydrogen market. Let's take an inside look at our team and facility at work.
Located in Dundee, Scotland, our 7,000 square foot facility provides a completely vertical approach for the development of proton-conducting ceramic electrolysis. We have assembled the right team, focused on hydrogen production, in a community determined to be globally recognized as a center of excellence in sustainable mobility. Materials purchased from valued partners like Praxair Specialty Ceramics can be measured for particle size distribution to control packing density and the microstructure of the electrolyte and electrodes in the cell. This data is recorded by our quality design program during incoming inspection to ensure quality and repeatability. Material measurements also help control the porosity of the cathodes produced by LERG, further ensuring consistency throughout our process. Our team has the ability to challenge concepts through EIS modeling and test these assumptions on low-cost, high-throughput button cells. Our button cell process provides the foundation for our research. We can rapidly test new ceramic chemistries for conductivity and performance in various steam and temperature conditions. This leads to a more rapid, low-cost decision-making process than using full cell production and test. These initial material studies are transferred to our in-house production team. We have the capability to mix the powders on-site and process them in our semi-automated extrusion equipment. This allows for accurate, repeatable manufacturing of our proton-conducting ceramic cathode. The process is captured and transferred to Kyocera for further improvement and scale-up studies. Our in-house dilatometer and simultaneous thermal analyzer equipment provide rapid answers to complex questions. The SDA identifies thermal events in oxidizing or reducing atmospheres and measures the change in mass and heat flow from a sample as the furnace temperature changes. The proper sintering profiles, coefficient of thermal expansion, and composition analysis, real-time, has played a key role in our success. The dilatometer information enables LERG to manufacture durable tubular cells by matching thermal volume changes during sintering of the cathode, electrolyte, and anode. Our cathode functional layer, electrolyte, and anode coatings adhere to strict quality control processes, which ensure high levels of efficiency and durability during tests. Measuring properties like viscosity of the slurries is essential for the control of the extrusion and coating processes during cell manufacture. We rely heavily on our QBD system and the raw data when transitioning to high-volume manufacturing with our partners. On-site application of our coatings allow us to rapidly iterate combinations of various coating chemistries. This flexibility drives improvement because modifications to chemistries are driven by data collected by our team in real time. We also experiment with stroke and dwell times during the process to accurately control the desired thickness. Material selection and application techniques significantly affect the performance of the cell. This in-house capability makes the capture and transfer of information to production partners like Kyocera possible. We fabricate end cap and cathode collectors to improve leak rates and cell performance. Understanding cell leak rates real-time at predetermined process checkpoints drives process improvement decisions. In-house brazing shortens the time to test and allows for valuable research and brazed materials applications. Our state-of-the-art single-cell test stands can emulate real-life reactor and stack conditions. These test stands allow us to change multiple parameters and optimize our operating conditions to increase cell durability and performance. Our stands can also simulate life tests on the materials that we use. We could then take the data off the single-cell test stand and use those same operating conditions and parameters on our stack tests. Once the cells complete their tests, we perform post-mortem analysis in our state-of-the-art analytical and optical lab. High magnification optical microscopes and our SEM provide large amounts of data on how our materials are responding to the environment in which they are operating. The SEM is an essential tool used to investigate materials for QC and to ensure cell layers are in specification. The SEM produces high magnification images of the ceramic surfaces, allowing LERG to determine the phase boundaries, porosity, grain size, thickness, and density of the layers in the cells. EDX processing gives precise elemental mapping of the surface. This function provides information on elemental distribution and diffusion throughout the ceramic materials. 3D mapping gives height, area, volume, and ISO-compliant surface roughness information. The ability for our highly skilled scientists to vertically integrate our R&D process in one location allows for an extremely high level of collaboration and rapid iteration of technology improvements. We feel we have the premier proton-conducting ceramics research facility in the world and are ready to conquer the challenges on our journey to success.
Hello, my name is John Hughes, and I'm the Vice President of Engineering at Low Emissions Resources Corporation. I'm here today to talk to you about the productization and commercialization of LERC's groundbreaking hydrogen electrolysis technology. Having proven the technology at the single-cell level, the next step towards TRL5, and ultimately to full productization, is the bundling of multiple cells together to create a reactor stack that produces larger and more meaningful amounts of hydrogen without introducing significant new energy losses in the connections between cells. To achieve this goal, LERC has partnered with Upstart Power, located in Southborough, Massachusetts. Upstart Power was formed in 2017 from a management buyout of the hydrocarbon-fueled solid oxide fuel cell business from Ballard Power Systems. Upstart Power is focused on the commercialization of SOFCs for industrial and residential applications.
As this presentation has shown, our team in Dundee has made substantial progress with proton conducting cell technology over the last 12 months. We've accumulated sufficient test data on individual cell performance and the optimization of operating conditions to achieve TRL 7 at the cell level, and we're currently pushing our single cell tests to 1,000 hours. Prior to the addition of catalysts, our cells showed energy consumption of about 45 kilowatt hours per kilogram of hydrogen. Initial cell tests with catalysts show improved performance in both energy and degradation metrics. Achieving TRL 7 classification at the cell level has proven sufficient reliability to now focus our efforts on stack and reactor development. This multi-cell stack configuration includes several design improvements from single-cell tests, including cathode current collectors, improved cap designs, and cell interconnects. We are currently running multi-cell stack tests at Upstart in Massachusetts. Successful multi-cell stack tests will demonstrate a TRL 5 level status. The stack design we are now testing is the first step in proving the scalability of our proton conducting cell. Partnering with Upstart in stack design allows us to expedite the foundational research and design modifications that can be transferred to our scale-up partners. As we look to the future, our cell research in Dundee indicates that there are still many technology parameters we can modify to improve our cell performance. Our coatings can be enhanced with recent new material discoveries. Kyocera is developing a process to produce a thinner electrolyte coating, which will reduce overall resistance. Improving cell ovality will improve system seal integrity and reduce system degradation. Additional testing will also allow us to further optimize the operating conditions and maximize the overall performance of the technology. Increasing the repeatability of the cells and improving the efficiency of the stack design will lead to larger multi-stack configurations and a future TRL 6 designation. We have carefully selected strategic partners like Upstart, Praxair, VHE, and Kyocera. These companies have many years of experience in SOFC and SOEC cell manufacturing, stack design, and plant design and construction. Each partner company has already developed a strong working relationship with our R&D team in Dundee. With our groundbreaking technology and the relationships we have with these industry leaders, we believe that we have all the pieces in place to develop the optimal solution to meet the increasing demand for green hydrogen production.
I trust you enjoyed that presentation. In closing, we have tried to show our vision to you of the hydrogen-based future. We've also shown you the high quality of the LER research and development efforts. You've met the leadership team and you've seen the work underway. The value proposition of LERC lays out as its accumulated knowledge and IP base, its fabrication process and the IP attached to that, and the PCC SOEC cell and stack performance levels, which are commercially noteworthy. The one-of-a-kind high-tech ceramics research lab and testing facility in Dundee, combined with the development partnerships with Upstart Power, Kyocera, and VHE Engineering, have come together to make great strides in moving green hydrogen synthesis into its logical next generation of efficiency. As we aggressively move into the next stage of commercial product development and scaling, we are looking for more partners to join us in this exciting journey. Please contact us for more details on the scientific data progress and the investment opportunities available. the need for efficient green hydrogen synthesis, and the role of high-tech ceramics make this an important moment in technological advancement. Thank you very much. As a pleasant postscript to this video, I would like to add our thanks to Scottish Enterprises for hosting the video, and also to especially thank them for very recently approving at the highest levels a significant grant to LERG for its work in hydrogen synthesis. Thank you for joining us, and thank you, Scottish Enterprises.
So, hi everyone. I'm Jill Simpson and I lead on the marketing and communications for the Michelin Scotland Innovation Park, working closely with Carrie, who delivered today's introduction. So thank you to LERG for preparing the video for today's session. I think we can all agree that it gave a really strong insight into their latest technology. And hopefully nobody is having any further technology issues as we progress into the Q&A part of the session. Thank you to our panel as well. So first of all, I'm going to moderate our panel session today. And thank you to the LERG executive team. So we have joining us for the panel session those who Carrie previously introduced: Richard Mearn, Jeff O'Leary, Joshua Persky and John Hughes. We're also joined by several of their science team who Jeff will bring into the conversation when required. So how we're going to do this, as Carrie previously explained, we have a couple of options for you. If you would like to ask a question, you can either raise your hand by clicking on the hand-shaped icon. I will then select an individual, call out your name and invite you to ask your question. And as Carrie previously mentioned, just to note that I will take you off of mute and there might be a slight delay, so just allow for that. Alternatively, you can also use the Ask a Question box and type in your question and I will read it out on your behalf. In the interest of keeping things smooth today, I will direct each of the questions to Jeff in the first instance, and Jeff will then bring in the appropriate panel member depending on the subject. We have until about 4:30 today, so just over an hour, and hopefully that is plenty of time to have a really good and meaningful discussion with each of you. So let's get started. First of all, hello and welcome to our panel. So I'm going to ask Richard, Jeff, Joshua and John to each take themselves off of mute, if that's okay. And I will say hello to each of you. Hello.
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 That's two voices. Do we have the others? Can you just check that they have removed themselves off of mute? So while they are unmuting themselves, I will come up with our first question. So like I say, raise your hand or type your question into the comments or chat bar. To get things started, I'll throw one at you first of all. So you've already shared with us the hydrogen-based future and your exciting new technology in your video. How important is it to you at LERG to work with others to help progress this next generation technology?
Okay, thank you for that question. As far as working with us, with our existing partners, it's incredibly important for us to do that because they understand the scale-up process better than our research and development facility does. So they give us guidance on what will work long-term downstream in order to scale up those processes that we're currently developing.
Excellent. Okay, and does anyone have anything else to add on the panel?
Well, this is Rich Marin. First of all, thank you all for joining us. And secondly, we will make available to all participants in this a link to listen to the video or look at the video in more detail. We know we threw a lot of information at you, so we want to make sure that you have the chance to review this at your leisure. To the issue of downstream partners, we really do believe we've picked world-class partners. Kyocera is probably the leading provider of high-tech ceramics in the world, and they are our manufacturing partner for this all-important ceramic cell that is really the heart of our SOEC system. Upstart Power, with whom we've been working for several years now, is a wonderful partner for building out the reactor stacks and dealing with a lot of what I call the productization capabilities. And VHE is a top flight Icelandic engineering company, is a company that has worked mostly with helping us turn our product into sort of an industrial grade capability with a demo plant and eventually a pilot plant. So we're really fortunate to be working with those caliber of partners. And what I would add is to say that we have plenty of room as we are taking this product forward into commercialization to talk with other potential strategic partners so that we can add to that array of first-class partners in taking this important technology forward.
That's brilliant. Thank you very much, Richard. And just to add that Joshua and John should both now be off of mute.
I am here. Yes, this is John.
Hi,
This
John.
is Joshua. Also off mute. Thank you.
I was in a
Excellent.
little
Apologies
panic.
for that. Yeah, that was me. I didn't realize I had to do it for you. So apologies and welcome. Thank you very much. So we've got quite a few questions have now come in. So our next question from Gary is, I used to use the Hoffman apparatus in my science class to demonstrate the separation of water into hydrogen and oxygen. Is this a much more complex way to get hydrogen?
Joshua, I think you're best qualified to answer that.
Yeah, I think solid state electrolysis is about the easiest way to make hydrogen in a green, efficient manner. Really, because we can utilize waste heat from other industries and electricity from any source. And in our case, the goal is to use electricity from solar or wind or other green energies. So the reactions aren't any more complicated than any other electrolysis process.
Okay, that's great, thank you. We do have someone who's raised their hand, but their name is coming up as Richard Marin. So I'm just going to unmute them, and if that is you, you should be off of mute. No, Richard, it might just be yourself.
I'm sorry.
No, I know, but you've come up twice, so I'll let you off. I've caused confusion. Otherwise, if I have if I've put someone's hand down accidentally, please type your comment and let me know who you are, and I will unmute you. So our next question is from Linda, and it is, tell me more about your stack technology and what gives you confidence it can operate at TRL5.
Again, that's for Joshua, since he's closest to that.
So I think our stack technology running at TRL5, the foundation of that really is the integrity of our cells, and we've pushed that into the TRL7 range where we've got a lot of confidence in the runtime and our QBD system looking at the quality of cells coming off the line. The second thing I think that's a good point on our stack is we've already begun demonstrating small scale stacks and running those. So we ran our first multi-cell stack a few weeks ago, and the performance of that stack was just in line with what we see during single cell testing in Dundee. That's a great sign. That means that the hydrogen production didn't suffer at all as we begin to scale up, and we'd expect that to continue as the scale gets larger and larger.
This is Rich Marin. I would add one other thing, and that is that while we've been working to get our ceramics to a TRL7 in Dundee for the last couple of years, we have simultaneously been working on an engineering basis with Upstart and VHE to take our stack design and contemplate all of the issues about the interconnects and the collectors and all of the things that otherwise increase the resistance and therefore reduce the efficiency of the system. And in doing that and thinking about it and spending a lot of time in the design stage over the last 2 years, it wasn't as though we waited until the cells were at their optimal level to begin that process. So we were overlapping and spending money to do the work ahead of the actual implementation of the stacks, which, as Joshua said, began on a multi-cell basis several weeks ago.
And if I could add one thing, Rich, and that is that an SOEC stack is not terribly different than an SOFC stack. And SOFC stack technology has been around for a long time, so we're not reinventing a wheel here. We're just optimizing the stack design for our particular application.
Well, and in fact, John, that's why we've used Upstart Power, because Upstart Power's expertise is indeed on SOFC functionality, and they work with some of the latest technology out of Kyocera in the full stack development stage. So that SOFC to SOEC learning pattern has been very, very helpful to us.
Correct.
Excellent.
I think that's good. That's a good point. We really leveraged a lot of the mechanical design and the thermal design from Upstart, and we kind of coupled that in the early days when we first started looking at these stack designs with CFD analysis from Fazil and some other partners. I think, Rich, that just kind of goes back to what you were saying before about the importance of the way we've structured our partners and the bigger team at LERC and LERG.
Okay, that's great. So our next question, we have a raised hand from Colin Arnold. So I am going to take Colin off of mute. Colin, I think you've also self-muted, so you will have to remove yourself from mute to ask your question.
Okay.
I can hear you. Excellent.
Yeah. Hi guys. Great presentation, great video. Question for me is, transitioning from R&D to volume manufacture can be pretty tough, especially for smaller companies. The video mentions that you're partnered up with Kyocera for high volume manufacture. So could you give us a little bit more on how you expect to make this jump from R&D to high volume, and how do you ensure smooth transfer of your technology to a volume manufacturer?
Well, to start off, this is Jeff O'Leary. To start off that answer, we've been working with Kyocera for about 18 months. We rely on their knowledge and experience to help us when we run into hurdles at the R&D level in Dundee. So things like ovality, that helps with seal integrity and repeatability. They're helping that out with us. They've already started with cell coating projects in their North Carolina facility, and that's to decrease the thickness of the electrolyte layer and just get a more manufacturable and repeatable process on coatings. We also started touching base with them on brazing, and they've done some experiments with extrusion as well. So we've brought them in very early in the process, so we're not developing something that can't be scalable. So we rely on that heavily as we go through each one of our processes. Josh, do you have anything to add?
Yeah, I mean, I think we've known that our mission from the beginning was to scale this technology, and so while a lot of university labs really focus on just the new science and the characterization, we were really fortunate when we built out the Dundee facility that we can make some strategic decisions about how that was set up and what equipment came out and how we built the team. So we were able to integrate our R&D lab directly into the pilot manufacturing facility. So there's no physical barriers or really intellectual barriers to that scale up for us. And then, like Jeff said, we started those conversations with our partners quite early. We've made it a real focus, to check in with those partners at each stage of the science. So, example, when we develop our extrusion batch formula, we're doing a lot of really fundamental science on the rheology and how those materials behave, and we're constantly checking back in with Kyocera to make sure that the dough recipe is compatible with their equipment. And then, in addition, the extruder that we're using in that facility is a small industrial piece of equipment. We already have all of that data lined up to know that it's a scalable process.
Excellent. Okay.
Yeah, thank you.
So our next question is a typed question. It is from Audrey, and it is, I noticed that your cell technology has advanced to TRL7. Can you tell me what the R&D team is working on now to further advance that technology?
Joshua, you can take that.
Yeah, I'd be happy to. Yeah, I think the team advanced the chemistry and the manufacturing process really quite rapidly over the last 18 months to get us this TRL7 designation. And I just want to say that's a really exciting achievement, I think, for the team and everybody involved. And that's the foundation of what's going to allow us to focus on stack and reactor testing, is knowing we have that good foundation. As important and as good as that accomplishment is, it certainly doesn't mean that the work in Dundee is done. The team's dedicated to moving us forward, I think, in 3 primary areas. They focus on interfacing with our partners on the cell manufacturing side and the scale up, and on the stack side with all the different materials and coatings and corrosion testing that goes into that. And they're constantly integrating those findings with the scientists in those companies.
Well, this is Rich Marin. I would add a couple of things to that, and that is that as in integrating the last 2 questions, actually, we originally thought that Dundee was going to be what I call a light manufacturing facility. And as we began to develop the cell technology, we began to see some very exciting abilities to constantly improve that technology through all of the means that Joshua and Jeff have mentioned, in terms of the types of catalysts and the types of fabrication technologies that we're learning about every day and breaking new ground on. And so we've created the facility as though it were an industrial grade, a small industrial grade facility, but then we shifted back to it being a laboratory and testing facility because we thought that one of the important aspects of this type of technological development is to constantly be improving the technology from a generation 1, 2, 3, 4, 5 and going forward, so that while we were having Kyocera as our manufacturing partner, build out volume of cells to do our first generation reactors, they would be busy in Dundee improving the technology so that Gen 2 was a quantum leap forward in terms of performance and indeed reduced cost. Because when you get to commercialization, as everybody knows, it's a combined benefit to seeing improved OPEX in terms of performance and improved CAPEX in terms of reduced cost. And we're able to do that much more effectively by keeping Dundee as a research and testing facility, while our manufacturing partners sort of crank out the cells and the stacks for commercial sale.
Okay, thanks for that, Richard. So our next question is a raised hand from Mark Selby. So Mark, I'm just going to take you off of mute and hopefully you will be able to ask your question.
Hello, afternoon. Yeah, I guess a couple of slightly joined questions. I think you mentioned a 50 cell stack, and I wondered if you could just comment on sort of the scale of power, electrical power that runs at, and is that the same as the scale as your planned demo plant, or is that multiple stacks? And then I wanted to follow on and ask about CAPEX and efficiency of that at that scale as a green electricity to units of hydrogen produced.
Okay, Joshua, do you want to start that answer off? Maybe we can transition to John or myself.
Yeah, I think I can give you an idea on what the plan is to scale up, and then I think, John, if you want to talk about the power requirements. The way we've sort of taken the approach to designing these larger stacks is to build modules that then get linked up either in series or in parallel to build bigger and bigger systems. As the manufacturing goes to higher TRL levels, that singular module will become larger and larger. So right now we're working in the kind of 5 to 10 cell range. We'll be stacking 5 or 10 of those together to make a 50 cell. Once we get the statistics down and manufacturing really ramps up, we'll just build single 50 cell stacks and stack those into the primary plant sizes. So this way, it really allows us to drive the cost down as we scale up and get all of the quality control and seals correct before taking on the very large commercial projects. John, you want to talk about the power requirements for those big stacks?
Well, I don't have the numbers in front of me. We have to decide really how many cells are going to be in the stack. As you mentioned, we've talked about 50 cell stacks. We've also talked about 25 cell stacks. So the absolute power is going to depend on the number of cells as well as the surface area of the cells. But in terms of the energy requirement to make hydrogen, we've got a target of somewhere in the 45 kilowatt hour per kilogram of hydrogen produced range. So you can do the math and figure out about what the total power for the system would be if we had 25 or 50 cells. And I can do that math during a break here if you want, but I think that the important number is the energy per kilogram, and so we're targeting something in the 45 kilowatt hour per kilogram range for our micro plant, which is the 25 to 50 cell stack plant.
Just to follow it up, one of our scientists had sent me a note now that it's about 3 kilowatts at 0.25 amps per centimeter squared for a 50 cell stack.
Okay. And I think it's important to know that the number that John is talking about, that 45, so we've actually demonstrated that a number of times on the single cells in Dundee. So that's, that's a good target for us, and it's a target that we have data that we've achieved.
And I think it's important to note that the thermodynamic minimum is something in the mid-30s, is it not, John?
Yeah, the lower heating value for hydrogen is about 34 kilowatt hours per kilogram.
And we do think that with the combination of catalysts and our electrolyte, and by Kyocera's ability to thin out the electrolyte layer and thereby reduce the resistance, while 45 is a level we've achieved so far, we believe that with that refined fabrication process and the addition of some of the very exciting catalysts we've already discovered, we'll be able to bring that down even lower.
It's also interesting to note that most commercial electrolyzers on the market today run in the range of about 50 to 60 kilowatt hours per kilogram. So we're very excited about where we are at the single cell level, and then at the stack level, optimizing the stack design to minimize electrical resistances will be key, so that we can have a product that runs in the mid 40s or better.
Okay, that's really helpful. Could you just comment on what temperature range you're operating in the map?
I think it's 600 to 650 degrees C. Is that right, Joshua?
Yes. Yeah. We're currently running about there, and that actually kind of brings us back to this idea of why we've coupled our fundamental science work with the scale-up stuff. We made a really exciting discovery earlier this year on optimizing that temperature through the fundamental science and running some EIS. I don't know, Richesta, if you're comfortable, if you want to talk a little bit about that. I know you just put out the poster and are in the process of writing a paper on some of that work.
Right. I guess the killer question is ultimately is what do you think at scale your cost per kilowatt of a system would be?
Well, I think the only thing we're sort of comfortable representing now is that we'll be able to be at 45 or lower on a system basis. As you know, there are certain stack resistance issues in terms of the interconnects and the collectors that we have to be a little bit careful with, because there's a cost benefit trade-off depending on the material you use. More expensive materials can give you lower resistance, but we have to find the right blend. And you yourself brought up the CapEx issue. We have to find the right blend between the CapEx and the OpEx. In general, we feel comfortable saying 45 or lower after consideration for all of the sort of optimized or minimized cost elements that we're trying to find in terms of the materials for those interconnects.
Okay, great. Thank you. I don't think I'm going to get an answer on that, Emma. But that's cool. It's fine. I know where you come from.
Okay, thanks very much, Mark. I will put you back on mute. And if another burning question comes up, feel free to raise your hand. So our next question is a written one. It comes from Nigel, who has asked, and I'm really interested to hear the answer to this one, actually. So as a US company, you will have had contacts in many countries around the world. So what was it that attracted you to Scotland as a preferred location for LERG?
Initially, we were attracted through the relationship we had with Professor Irvine at the University of St. Andrews. I mean, they have a leading group of students and scientists at that facility in this area. So that was kind of like a launching point for us. We had I believe about a 300 or 400 square foot lab there, and we expanded from there about a year and a half ago to our current facility, and we still have that relationship intact by sponsoring students and working with Professor Irvine on a routine basis.
Well, and I'm going to add that since I know our entire staff in Dundee is listening to this, a lot of it had to do with the very, very high quality of people available, many of whom came out of University of St. Andrews, and that being an interesting locus to get the kind of intellectual capability that we need, and the skill set capability was a very big part of locating in Dundee. Now, as it turns out, if you read the IEA report from last year about the future of hydrogen in the entire energy complex of the world, they indicate that the North Sea area is indeed the focal point of almost all of this future activity in their estimation, between the activities going on in the Netherlands and Norway and in Scotland. And I would love to tell you that when the decision to go to Dundee was made, it was because we were totally prescient about where the future for hydrogen was going to be located, but that would be far too bold. We got very lucky because Dundee is indeed ideally located to be at the center of this new hydrogen economy. And so we're happy to be both a little bit smart, but very lucky at the same time. Plus, Dundee and folks like Scottish Enterprise have been so incredibly helpful to us, as has the UK government, that I'm thinking of switching my citizenship from the United States to the UK. And actually, I should say to Scotland. I don't want to call it the UK just right now with everything going on in Scotland these days. But we're very, very happy to be located where we are, and think that the interest in this technology resides much more importantly between the UK and the EU than it does almost anywhere else in the world.
Excellent, thank you. You're more than welcome. Come to Scotland. I think everybody should come to Scotland. We're very welcoming. And I have to say, as a fellow St Andrews graduate and a huge champion for Dundee, I could only agree with all of your comments. So we're very glad to have you here. So our next question is a raised hand. So it's from Bercest. I will unmute you now. Now I think you have to unmute yourself as well. You're self-muted, so if you just unmute yourself. There we go.
Hello, this is Barjesta from LERC. I was actually raised the hand to when the Joshua sent the question about our working temperature. I want to mention that it's just previously we were working at the lower temperatures, 550, and then we had a degradation problem. Our electrolyte is actually quite conductive even at the lower temperatures. So this is why we were happy with the working on the lower temperatures. But then we had a degradation problem, and then we start to some test under the electrochemical impedance spectroscopy, and we tried different atmosphere and then different temperature, and then we noticed that actually our working temperature has caused the degradation, but above at the higher temperature, we sorted out this degradation problem, and we see no degradation, no remarkable degradation for 100 hours, and under the EIS. And then we applied these results to the single cell testing, and we managed to solve our degradation problem. This was what I want to say to add to the Joshua's
Thank you.
comments.
Thank you.
That's great. Thank you very much. Has the panel got anything else to add to that one before I move on to the next question? Nope.
No, I think we're good.
Excellent. So our next question is from Gary, and he has written, I did not see any method for converting the hydrogen gas into liquid at very low temperatures. Do you have any comments on that?
Joshua, I think you should take that.
Yeah, so our plan right now is to really deliver the hydrogen to the customer and let them deal with that side of the balance of plant. So we don't have any liquefaction or really even any high compression planned for our technology.
John, do you want to add to that at all?
Yeah, again, as Joshua said, it's application specific. If you want to put our electrolyzer in front of a refueling station, you'll need to cool it and compress the hydrogen before loading it into the vehicle. But if you put our technology in front of a Haber-Bosch plant, you want your hydrogen already hot and pressurized. So, we're not looking beyond the hydrogen synthesis portion of the plant just now. We're synthesizing hydrogen and allowing the customer to decide how he's going to handle it downstream.
There is the possibility of running it at moderate pressure so that we're delivering some pressure head. Of course, one thing you have to remember about high temperature electrolysis is compressing gases at high temperature does take a debit on the efficiency. So our goal is to deliver the hydrogen for whatever process downstream is needed, and then let the customer make those decisions.
And I'm going to add, at the risk of tiptoeing into the technical arena, and please correct me if I'm wrong, but we want to point out that one of the beauties of the PCC approach is that we end up with pure hydrogen. And unlike, say, PEM, where you need to, necessarily go through a liquefaction process to remove excess water and whatnot, or certainly in the SOEC oxygen methods. This way, if you have just pure hydrogen, you have more flexibility, as John said, to use it in whichever manner is most applicable for the application you're dealing with, right, John?
Yeah, and if you desire cooler hydrogen, our plan would be to run the hydrogen as well as the oxygen and unutilized steam through heat exchangers in order to recapture as much of that thermal energy as possible, and use that to preheat water and fresh steam going into the reactor.
That's great. Okay, so we have another question that's been asked from David, that is, how might a company collaborate with LERG? I run a company that has advanced electrocatalyst products for a wide range of electrochemical processes. We may have something, products or capabilities that might be of interest.
Okay, I'm sure we can figure out how to get our two companies in touch with each other and discuss what opportunities are out there. We'll be sending a packet out to everyone that's on this call after the call, and then John Hughes is in charge of business development on our side, so he'll be taking any after session questions or comments, and he can get back to you and put you in touch with the right person in the company.
Excellent. And I guess, Jeff, that goes for everyone on the call, that yeah, you would like to hear from anybody that wants to work with yourselves on new technology or ideas.
Yes, this is true.
Yeah,
Yes.
absolutely. We'll follow up with all the participants, and we'll give you contact information. So if it's a technical partnership, that's one thing. If it's a financial partnership, that's another thing. But you'll have contact information, and you'll know how to get a hold of us.
And that follow-up is also going to have some data that will help you on the technical side understand where our value proposition is.
Okay, I think that will be very much appreciated from all of the attendees. So thank you for the efforts you're putting to prepare that packet. So we have another question asked from Audrey, that is, what are your plans to get the stack testing to TRL6 and beyond?
Okay, John, can you explain to them how we've been working in parallel on that design?
Yeah, sure. Yeah, so while the Dundee team continues to optimize the individual cells, the stack team is going to be focused on several things. In the near term, say the first 1 or 3 months, we'll continue to work on improving the energy efficiency of the stack by minimizing all the electrical resistances, while we're also focusing on improving the brazing materials and the processes for better seals. In the midterm, say 3 to 6 months, we want to increase the cell count in the stack, either by making larger manifolds, which can hold more cells, or by fusing together multiple small stacks to make a single 25 or more cell stack. And then in the long term, say 6 months or more, we plan to demonstrate this larger stack in a self-contained standalone micro plant that has all of the balance of plant components, meaning a steam generator, rectifiers, heat exchangers, etc. And in fact, in conjunction with our plant design partner, BHE, we've already done a lot of the basic design work and much of the fabrication work for what would have been an ammonia micro plant. So it really won't take a lot of effort to reconfigure that as a hydrogen microplant once our stack refinements are complete. And at that point, we believe we will have demonstrated a TRL6 level for the reactor and stack.
Okay, that's great. So our next question, I think we have one that will be asked from Kevin Basley. So Kevin, I'm just going to take you off of mute, and if you can unmute yourself as well, you should be able to speak.
Thanks, Jill. I was reading the European hydrogen strategy, and there's a target in there for 6 gigawatts of hydrogen production by 2024. How realistic do you think that is, and do you think you guys can be contributing?
Yeah, that is our goal, to have a product commercialized before that point in order to play in that market. It's one of the reasons we're investing so heavily and working so hard to figure out a new way to make green hydrogen. Rich, would you like to take that from there?
Sure. I mean, I think there's always a tug of war that goes on in product development initiatives like this, of when to come out with your Gen 1 product and how actively to spend your time trying to sell into the commercial marketplace versus wanting to always improve it 1 step or 2 steps more. We have to play that a little bit by ear, but we're hoping that we'll be ready by the end of 2021 to have a commercialized product that people will be able to actually, write orders against. Our ideal situation is to work with strong partners, and part of our outreach here is to hopefully interest some strong partners in the same way that we're working with Kyocera to manufacture the cells, with a strong partner to manufacture the reactors. Because in many ways, we're not the optimal shop. We're a research and development shop. We're not the optimal shop to build out or even commercialize the sale of these reactors. So we suspect that we will find a good partner in the near term that will be working with us to find the right balancing act between commercialization and further development, and then be able to time our market entry with some good, strong initial clients that will, validate the full commercialization of the product. I'm expecting that to all unfold in 2021 as we've gone well past proof of concept and proof of commercialization capability. And I think that means that by 2024, and very much in keeping with the timeframes in the IEA reports and the initiatives underway, we will have product that'll be available. I think for us, because ceramic cellular technology is still developing, it'll start with sort of the distributed end of the spectrum as opposed to the large industrial end of the spectrum. If I were targeting in a betting man, I would tend to say we're more likely to have wonderful distributed hydrogen synthesis mini plants, not micro plants, but mini plants that would sort of be for refueling stations first. And then as this technology proves itself out at that level, moving into a full industrial stage where we are working with major ammonia plants and other industrial applications like that, where we're replacing methane steam reforming capabilities with green electrolysis hydrogen capabilities. That will be several added years beyond that, as industrial plant scale requires some more refinement of a lot of our technology building. Luckily, there's been so much balance of plant capability that exists already out there. Many of the people we've talked to as potential partners have said, you bring us the performance capability of ceramic cellular technology, we will help take it for CapEx purposes into a more industrial scale balance of plant capability. And that's what we're counting on. So that's the way we see the future. 2021 being the year when this moves completely from, I'll call it the lab and testing facility, into a full commercial demonstration capability, and then preparation for marketability.
That's great. Thank you, Richard. So I'm just going to ask now, is there any other questions for our panel? There aren't any hand raised, and I have worked my way through oh, look, there we've got another hand raised. So Colin Arnold, I will unmute you now if you unmute yourself.
Yeah. Hi guys. Yeah. Just a question. Just through the video, I mean, my background's in lithium cell manufacture and scaling up to volume production. So I've heard in the past that there is, different technologies, but a bit of synergy between the two processes. And through the video, I just heard lots of phrases, cathode, anode, slurry. Just wondering, what your thoughts are on that. If you do think there's a bit of synergy between the two kind of technologies.
Josh, are you familiar with that?
Yeah, so between which two technologies, ours and which one?
Well, like like lithium cell manufacture, scaling up from chemistries. So you're creating a slurry, you're coating electrodes and anodes and cathodes, and then making cells. So I was just wondering if I've heard it before that there's meant to be some synergy between the two processes, but I know they're different technologies.
Yeah, I'm sorry, I'm not real familiar with the lithium cell systems, but I can say, from a scale-up perspective, the dip coating and the spray coating and a lot of these ceramic processes that we use to make our cells are already done at very, very large scales for other technologies.
Yeah.
But there's no fundamental barrier to scale up there.
No. Have you got a special operating environment during the manufacturing process? Is it in a kind of clean room or a dry room, or is it just in normal factory conditions?
Right now in Dundee, it's really just normal factory conditions. As we scale up, it'll get closer to, in ceramic processing, we often call it a clean room, but it's not semiconductor clean room. What you
No.
want is a dust-free environment. You're laying down a liquid film to make a 10 or a 20 micron electrolyte. You need to ensure that dust in that area is much smaller than the thickness of that coating. But again, these class 10 clean rooms with bunny suits that you see, things like that won't be required.
Okay, thank you.
Thanks, Colin. Are there any other questions for our panel today from anybody on the call? I don't see any more, so just while everybody gives it one final thought, I just want to check with the panel themselves. So have you got anything else that you or perhaps your wider team would like to add as some final thoughts to today's discussion?
Well, let me jump in. This is Rich Marin. First of all, thank you everybody for participating. This has been an important opportunity for us to lay out our capabilities. And I think you can see that with the quality of the research and testing facility and the wonderful partnership we have in Dundee with the City Council of Dundee and with Scottish Enterprise and the UK government, we believe we have broken incredible new ground in the area of high-tech ceramics for this specific application. We originally worked on ammonia. We shifted with the world to focus on hydrogen, since that's the first stage in ammonia anyway. Our expertise is in both arenas, but it's always focused around high-tech ceramic cell capability. We appreciate everybody coming in, joining us, but we will appreciate it even more if you follow up with us as we reach out to you and we find ways to work together. So thank you very much. Thank you, Scottish Enterprise, for your magnificent grant that you've awarded us and for hosting this presentation. And thank everybody for joining in, and we look forward to increasing our dialogues with all of you.
Thanks, Richard. We've had one more question added in, so I will ask this one and then we'll do final wrap up with the rest of the team if anyone else has anything they would like to add. So Mark has asked, could you comment on the total size of the R&D and engineering team?
Yes, I mean, right now we have 7 full-time employees at the lab in Scotland. We have additional 2 people that go back and forth between the States and the lab in order to help out. But then, we complement that with basically our hub and spoke mentality of relying on our key partners like we've been saying, Upstart Power, Kyocera, Praxair, VHE, in order to help us move things along whenever there's a hurdle that we're having issues with. So in general, we have a pretty broad base of talent that we draw from, and it's helped us move along quite rapidly over the last 18 months.
Using dollars and cents as the measure, for every dollar we spend on our dozen or so employees, we spend at least $1 on the work that's being done at Upstart and VHE and Kyocera. So I like to say that we're about in terms of an FTE basis, we're about a 25-person strong effort, about a dozen of which are technically on payroll and on staff, and the other half of those people are people who we pay for through our partnerships. And modern business operates much more on a distributed hub and spoke basis that way nowadays, so that shouldn't be unfamiliar to anybody.
That's great. Thank you for that. So Jeff, do you want to add anything, any final thoughts to today's session and the discussion that we've all had today?
I just want to say the same thing that Rich said. Thank you very much for hosting this. Thank you for all the attendees who've decided to listen to what we're working on, and we look forward to continued dialogue with anybody that's on this call, and hope to expand that conversation.
Brilliant, thanks, Jeff. And likewise, John or Joshua, do either of you want to add any final thoughts?
I mean, I think final thought would be to thank everybody. And again, if there's any more technical questions, feel free to send those through. I think John's going to consolidate them and can distribute them. We'd be happy to get back to anyone interested.
I'd just like to add that we are very excited about the promise of this technology and the energy efficiency gains that can be realized, and we look forward to furthering this conversation with anyone on the line that is interested, and growing this business over the next few years.
That's brilliant. I think we can all agree we've had a really good discussion, lots of interest. We've already received a couple of messages saying what an excellent webinar it's been. So I would like to take the opportunity to thank you as a panel for giving us such an insightful discussion today. It's been really brilliant, both with the video that you pre-prepared and the information that we sent out in advance, as well as the discussion that you've participated in. So thank you all very much. And thank you also to Carrie for making the introductions and setting the tone for this afternoon's session. And as well as that, thank you to everyone who has attended, and whether you've listened or participated with questions, it's both very valued, and hopefully it's just the start of a really good and meaningful discussion with LERG. So as Carrie mentioned, the session has been recorded today. So I will share a link with you all after the session, and you feel free to share that with any of your friends or colleagues that you think may be interested. As well as that, Richard's already said that they will be following up directly with further information, and that will give you the opportunity to pose further questions if you think of something after the session. So other than that, I'd just like to say thank you, and to everyone, take care and goodbye. So have a great afternoon and evening, everyone.
Stay safe.
Thank you.
Thank you, everyone.
Goodbye. Thanks.
Thank you very much. Bye.